I'm with it. All right, so I'm just gonna start at number one, and just interject or do whatever you want to tell me what you need here. So, is it possible for an object to receive a smaller impulse from a larger force than it does from a small force? So yes, of course. So these are the equations you need. I'm gonna write vector notation here. I don't recall how you do it. It's usually that mass times velocity, but also J. Is that what you guys have? Does that sound familiar? J. Actually, it might be good to have your equation sheet. What is your equation for impulse? If you could just tell me so I can make sure to use the same one.
The equation for impulse is okay, I think it's delta T equals F times T or something. Yeah.
So what was it? Delta what equals F times T?
Delta lowercase p equals F times T.
Gotcha. So you're not calling it. Okay, so and these two, by the way, you're gonna want to know these. Like if somebody asks you momentum or whatever, momentum or impulse, you say immediately delta P equals F times T, right? So okay. Just a heads up. Force, the same old force you've been using. This is a time interval. It's not just, it's a time interval. So over some amount of time, 5 seconds, right? You're familiar with that pretty well by now. 10 seconds, I don't care. 20 hours, doesn't matter. It's a time interval, a period of time. This is a change in momentum. It's pretty important. And so what does that delta mean? Same old thing as before, P final minus P initial, again, as a vector, just like same thing as delta V equals that, a change, a difference. And so, I mean, that's what this first page is, just getting a bit of explanation and information about this. Let's make it real clear for you. Momentum. Try to remember these again. And so it's asking so to receive a smaller impulse from a large force than it does a small force, but they're asking for, okay, a smaller impulse. So this is just the direct relationship, right? What happens to the impulse as F is really big? Well, it's a multiplication. It's not divided by. So that means this is really big. But it's not the only thing that matters. It's the time interval. So because impulse is a product, it's force times time, is force over a time period or multiplied. That's what the equation means. And so let's say I could have the same exact impulse, from large force, small time. Make sense? As a small force over a long time. Does that concept make sense? It's okay to spend some time on it because this is in physics a lot. It's just talking about proportional relationships, right? Small time. Does that make sense? Because of this equation here. So maybe we get some numbers and it'll make more sense, right? But so how about what's a large force? 100 newtons, sure, right? And then what if I from Newton's laws, I'm pulling on this thing, pulling the rope, and I pull with this force for how long? A second, let's say, not very long. Large force, small time. But now let's say I only do 1 Newton. That's not very much. It's like the weight of an apple is 1 Newton, right? But say I do it for a minute and whatever, 40 seconds, 100 seconds. Well, the impulse is the exact same. Why? Because impulse is force times time. Does that make sense now?
Yeah.
So that's what this means. And if you can understand this part here, then you understand impulse. And that's what that number 1 is. Kind of, I mean, they're asking, can you get a smaller impulse from this larger force? Well, if you act over a very short period of time, if you just kind of, just push something with your finger, but you do it for a day, well, you're going to have a huge impulse, even though it's a small force. And so you smack, you Will Smith smack right there. And that's a second, right? Same impulse though, as if you're just kind of pushing his face for a day, right?
Yeah.
That's what impulse is. Again, but this is a change in momentum. So these things are closely related. Momentum and impulse are closely related. Okay, number 2 is two people of identical mass jump off a cliff. One person lands in water while the other lands in solid rock. Ouch. Which person, if either, receives the larger impulse? So this is just the same exact thing we're talking about, but let's go slow and be careful. So we'll say person 1. Who does it? Which person while the other lands on solid rock? Water. And then rock. I don't want to get too into this, but going back too much, but we actually do know the force in this thing. When they hit the water and the rock, it's the same distance, right? But from Newton's laws, F equals ma, or mg. The force here is your mass times the gravitational acceleration.
Mm-hmm.
For both people, they weigh the same. Guess what? Mass is the same, g is the same force. Why? Because that's what force is. You know that well. Okay, but they're not asking about that. The force is the same, awesome. But now, that's actually the second part, and this is the reasoning. But now, what is the impulse? And you say, well, I don't know. Same, but then, okay, you ask yourself, what is the equation? Oh, there's always an equation. We already know this is the same. Now, hopefully, you're starting to see here. Well, it depends. It's going to depend on the time. If the time, and so this is not the time for the fall here. That's not time. It's the time that the force acts. When is the force acting? This person is jumping into the water. The force of the person on the water. Guess what? Newton's third law says whatever force that person, this force here, whatever force that person gives to the water gives it right back. That's Newton's third law.
Mm-hmm.
And so, you've jumped into a pool and pour some water. And so it doesn't take very much time, but you can calculate it. And if you got a really nice engineering thing, you're not having fun and you're just measuring the time it takes the person to go into the water at that instant and you're not jumping in and partying or whatever, like you can measure that time. And so that's how we think about it. And the water is going to be a little bit slower, right? Because the rock, you die because that's instantaneous. You hit the rock, bam, that's such a short amount of time. But with the water, imagine there's a little bit of drag. If you think through it, you hit the water, kind of your feet hit first, and then it hits your legs, and then you're slowed down over time, right? So the force is decreased and the time is extended. So smaller force over time, but the time is longer. But that's it. Just boom, whatever that is, a millisecond, all at once, all that force at once. So larger impulse here. And it's just kind of a thought experiment for, do you understand impulse? Any questions on that?
Okay, so the rock, like hitting the rock is has a larger impulse because it's just kind of like instantaneous, I guess. Like you don't slow down as you hit. Is that what you're saying?
Yes. So this time here is when that force acts, the time period over which that force acts. And like you just said, it's instantaneous. That force of FMG just it's carried out almost instantaneously when you hit the rock.
Okay.
But then when you hit the water, that same force is carried out over a longer period of time. So I got it backwards. Same force, longer time. So the water has the larger impulse. I don't know why. Sorry. Because it's a product here. If the force is larger, the impulse is larger. If the time is longer, then the impulse is larger.
Okay, so
sorry, I got it backwards.
The water is a larger impulse?
And the only reason is because it takes a longer time to kind of deal with that force. Like you said, you understand as you hit the rock, you have a force on you and then it's gone immediately because you hit the rock, then there's no more force. You're just laying there with whatever, you're just laying there broken bones. But like with the water, you have the same force, but then it takes longer for that force to kind of dissipate or for the water to absorb that energy.
Okay.
Short time, same force. This is longer time. Same force. And remember, the product of these two things, time multiplied by force, is impulse.
Okay, so both of them have the same force between them. It's just,
Yes, that's exactly right. The time, it's the same force, right? Because he's falling, and it's mass times acceleration due to gravity.
Mhm.
But the time period is longer for the water. Right?
Okay. So,
Sorry, my thing wasn't plugged in, and so
oh, okay.
I'm charging it now. So I thought I was charging it, but now it's, yeah.
Um,
Does that kind of make sense? It's okay if it's still a little unclear, because we're going to get into the problems, and then hopefully it kind of drives home.
okay, so the larger impulse means like, I guess I'm just stuck on the word impulse because I kind of forgot like what it means.
It is force times time.
Oh, okay.
It's
Okay.
exerting a force over a time interval. If
Okay.
that helps, you seem to like that example. So like, imagine just, pushing your finger really lightly on exerting some force, but for a day, it's a force times a time. I'd give 1 Newton to my television screen, but over a day, that's a big impulse, even though it's a small force, long time. Will Smith
Oh,
smack, that's a large force over a short time.
yeah. Okay. Oh, okay.
And
So that makes sense with the water. Okay, gotcha.
yeah. Okay, good. It's exerting a force over time interval. Okay, cool. Sorry, I'm waiting for this thing. This should boot up any minute here. So I will just kind of move to number 3, since that's what you did there. Or actually, okay, so I'm going to go to the momentum page because it's more explaining. So I'm talking about the 747 jumbo jet, which has greater momentum. So it's kind of the same idea as impulse. What is momentum? Well, mass times speed.
Mhm.
If you have a large mass, then you have a large momentum. If you have a large speed, you have a large momentum. But it's the product of those two things, right? So that's what it's saying. A car speeding down the freeway, how much does a car weigh? I don't know, kilogram, not a kilogram. It weighs, I forget. It's like a ton or something, right? I forget what that is in kg. And it's moving really fast. So it has kind of a large mass and a pretty fast speed.
Yeah.
Jumbo jet, I don't know. That's probably like 1,000 cars, right? It's way more massive. It's
Yeah.
moving a lot more slowly. You've been on a plane, it doesn't go that fast. We're not talking about takeoff. We're just, it's taxiing, right?
Yeah.
But that 747 has way more momentum. Why? Because momentum is a product of the mass and the velocity. And an impulse is basically the same. If you understand the relationship of momentum equals m times v, then you know the relationship of impulse equals F times t. It's the same relationship, just different quantities.
Okay.
Okay, so we can get into this one here. It should be any minute now. So Skydiver without a parachute. Assuming the Skydiver is number 3 on impulse and momentum. I'll definitely come back and fill in the gaps here, but we do have some stuff here. Assuming the Skydiver has a mass Awesome. They give us a mass. You write that down. And a terminal velocity. So he has a mass and a velocity. That's it. That's all we're given. Oh, and then they have to know what to find. Momentum before impact. Okay, so first thing here, do you know what terminal velocity is?
Oh gosh. I don't remember.
So you remember free fall? And like you keep speeding up, right?
Yeah.
If you drop something from rest, it's going to be moving really, really fast at the bottom of its thing. Same with conservation of energy.
Oh, yeah. Okay.
Because it's accelerating, right?
Yes.
Acceleration means increase. Well, it means a change in velocity, but you drop something, and the only way is if it accelerates, the speed increases. So given that, you say, oh, I'm going to apply free fall to jumping out of a plane. But it's there's air resistance, right?
Yeah.
So there's a maximum velocity. That's what terminal velocity is. It's the fastest you could ever go. You don't just keep accelerating in the real world.
Yeah.
Okay, so that's the fastest you could possibly go. And so, I mean, what it's asking here is m times v. Why? Because they want the momentum before impact. We know that the velocity keeps getting bigger and bigger and faster, but not at terminal velocity, because that's the fastest you can possibly get. So that's why momentum here is m times v, 85.5 times 135.
Mm-hmm.
Simple as that. That's the first one. That's always momentum. It's mass times velocity. So 60. What is that one? Does that say 135? I forget the thing for mph to meters per second.
He changed it to 135.
Oh, I see. Okay. So yeah, you do have to convert that, obviously, because if you're in kilograms, well, you better go to meters per second. I mean, you should convert it all to SI, because the standard, I forget what that stands for, but it's SI units. And so, okay, that's right. So 135 is actually 60.4 meters per second.
Mm-hmm.
And that's why it looks like you accidentally wrote P equals 60.375. It's actually the V velocity equals 60.375. There we go. I'm going to write this down in just a second. But then after that line right there, it says P, boom. What is P? Mass times velocity. You just spent all that time in work calculating velocity from meters per second. Now you just multiply, just a product. Apparently it's 5162. But remember, momentum is a vector. It's in the same direction as velocity.
Mm-hmm.
That's why there's a minus sign. Velocity's down, right? You're going towards the earth. It's usually down, minus sign. Momentum is the same direction as velocity. All right, here we go. I'm going to write this stuff down for you. Oh, got to reconnect. So that's why it's minus 5162. And the units actually are kilograms times meters per second. Why? Because it's mass times velocity. Kilograms are the units of mass, right? Fairly straightforward. Oh, I gotta I'm gonna exclamation T. All right, and then here's the thing. So that's momentum. Great, we did that. And then they're also asking for the impulse and the force, right? So impulse is a change in momentum. This is where I should write it down. But you already have the final momentum. Does that make sense?
Mm-hmm.
Because it's minus 5162. That's just before you hit the ground. What's the initial momentum? Well, it should be 0, I think. Because imagine jumping out of a plane. You're not moving. You're not moving down. You're just like if you dropped a ball. Yeah, makes sense.
Yeah.
And so the impulse is a change in momentum. What's the change in momentum? Well, let me write it down, but it's the final minus the initial. So minus 5162 minus 0, so it should be minus 5162. And that's the only case if you have initial momentum 0 or final momentum 0. Because otherwise you need to subtract.
Okay. Are you sharing your screen?
Sorry, I'm waiting for it to boot back up. Boot up.
Oh,
I'm
okay.
waiting for it to turn on again. Yeah, I definitely want to write this down for you. I'm just an idiot today, I guess. Stay code. Got it. No audio. Okay, hopefully you can see this
Yes.
again. Make sure it doesn't come out again. So I'll briefly go over that again if you want. Does that make sense? The situation, they give us a mass.
Can you go over like the last part that we were talking about?
Yeah, sure. Oh my God. So impulse, we got to write this down. Oh, that's what I got to do. Oh, that's what I got to do. Okay, I'm back. Is this sharing? Can you see that writing? No.
No, not yet.
Okay. Start there. Okay. So that last part we were talking about, they want us the momentum again, please. M times velocity. We got that. What is impulse? It is a change in momentum. What does this delta P mean? Well, it's F times T, as you said, a force acting over a time interval, but it's also, well, the definition of delta is a change. So what is that? So P final minus P initial. Initial momentum, final momentum, just like you've always done. What is that actually though? It's M times final velocity, right? If P is M times V, well, now I can just do my subscripts like always, right?
Yeah.
M times VI, initial velocity. And so you can also say it's M because the mass never changes. The mass doesn't change from initial to final. And so you have that. So a change in velocity is actually a change in momentum, which is an impulse. So impulse is also that, but it's also this. That's just your general stuff. But as we were saying before, well, V initial 0, we should assume, I'm pretty sure. V final, well, whatever it is, 60.375. Or more importantly, this thing for the problem is M times VF minus 0 because VI is 0. So the impulse, which is a change in momentum, minus 51.62. Same units. Make sense? Kind of.
Yeah.
So, and then we have to, how'd you get the force here? Oh, force divided by the time. Where'd you get the time? Time average. Fine. Where'd you get those times? 1.19, 1.2.
I think that okay. So we watched this video and that's where we got some of the information. And then he had some of us like time how like what we thought it would be.
How
like
long it took him to get to the
Yeah.
plane to the ground?
Yeah.
Or terminal velocity, I guess. Okay, makes sense. So that's hopefully you really understand, because I had to ask you, what's the time? Why? Because we just solved. I'm going to take you through what we did here. We were given M and V. We can always find momentum there. Then they ask for impulse. That's the general equation, but then you say, oh, but it's also a change. That same stuff. Oh my God, you gotta be kidding me right now. I don't understand why my thing keeps dying. That really makes me angry. Okay, I'm gonna have to do what I did before and sorry, we'll do this and just tell me if anything is weird. This is what I was telling you about. The momentum, of course, and then we say, oh, we want an impulse. So how do we do that? Well, impulse, as of course, is this F times T, but it's also what we just said, right? A P final minus an initial. But then, so these are the two equations that we're working with. Great. We found impulse. Remember, it was whatever is minus 5162 because the initial momentum is 0.
Yeah.
So we want the force, but that's why if we solve for it, we have to have a time, because the impulse is a force acting over a time interval. And that's why we had to have that.
Yeah.
So that's part of it. And that's kind of the simplified thing, which you based on what you've told me and have you told me you've been doing well, all that makes sense. And it seems pretty straightforward. Is that true? Is that true?
Mm-hmm.
Okay. And then the average time is the other thing there. You want to take the average time interval. And that's why you did this whole thing, right? Where you said, T1, that must have been your first guess or something, or somebody else had a guess. There's 4 times there. 1.19, and then there's T4, and you just take the average of all those, which is a useful thing that you do, like in lab especially, but also here you want to just average everything out, especially if you have just an initial and a final. So that's actually everything for that one. Is that one clear now?
Yes.
And can you see what I'm sharing right now?
Yeah.
Okay, I'm gonna go up to number 3 here. This looks like a little more difficult, but it's number 3 on impulse. I'm sorry, yeah, number 3 on impulse and momentum, the 1.4 kilogram baseball. So I always do this. I will never not do this, and I hope that you do it as well. Every time you see something, you write it down. We got a mass of a baseball, 0.146. And it's moving towards the batter. Okay, so we have a velocity. I'm not sure if it's the initial or final yet. We're going to write it down as, whatever it is. Hopefully that's all straightforward stuff that you do every time. Swings the bat and strikes the ball with the force. So we're given what? A force also. So you write that down. So we're saying minus 1200. Okay, that minus sign's a little weird, but now that if we think about this equation, which you would write down or choose, I mean, this is going to come up, the impulse equation, which is a change in momentum or impulse, same exact thing. Change in momentum is impulse, is a force acting over a time interval. And so when we see this change here, this delta, this minus sign here makes a little more sense.
Mm-hmm.
The ball leaves the bat traveling in the exact opposite direction. So normally you'd have This is what I like. This is what you I like to do for momentum problems. Is to have like an initial, you say I for initial, just write I. I think we did this for energy. So yeah, that's good. If the batter's here on the left, sorry for the best I can here, but the ball is initially traveling to the left, right?
Mm-hmm.
And these minus signs, you're going to want to, since we normally call the negative direction left, let's just have it travel right. And the reason is because this second thing tells me that it's traveling -50 in the opposite direction. So we'll say positive to the right here. And then he swings it back in the opposite direction, -50 there. So we actually can, here, I won't go too quick. This is unusual. So that's the final situation. Just the batter hits it to the left, opposite direction. I will say that it doesn't matter if it's left or right. It just which direction do you want to call positive? That's really what matters. Do I need to clarify anything here?
No.
Okay. And then let's be a little bit even better. A little baseball. Okay. That's not complete garbage. And then baseball gets hit to the opposite direction. There you go. We got the force. So I'm going to go back up here because we are given, if we go back to our things, a 0.146 kilogram baseball travels toward the batter. Okay. And I realized the ball was kind of weird. That's a momentum vector. The ball is traveling to the right, and then it gets struck, and then it travels in the opposite direction. That's the initial velocity of the ball.
Yeah.
And then we're given also traveling in the opposite direction. So we would have a V final here. Really important to know your subscripts because impulse is a change of momentum. That whole thing we went through. And so how long the bat and ball were in contact for. So again, the equation you have, you need both of them, MV. But like we said before, the momentum, or the change in momentum is also impulse. So these are your two equations that you give, delta P. Let's write this first, because I know it's on your equation sheet, but you don't ever want to forget this, that that's actually truly what delta P is. It's a change in momentum, which just turns out to be F times T. Is all that clear so far?
Yeah.
Okay, but before you actually use your equation sheet and look at that, I want you to say, oh, but what is P final? Well, it's M times V final. Why? Because momentum is mass times velocity minus M times V initial. So I've just literally from here to here is just plugging that in, this equation for momentum.
Mm-hmm.
I will try this one more time. So I think it's a little better, but and now hopefully you can see, okay, let's write down the equation that we actually kind of have here. and one that's super useful for you that we haven't even plugged in any numbers, but it's just true, right? Well, M never changes. The mass doesn't depend on the initial and final points. It's always the same. So we can factor out things that are the same and get that. And so that's the kind of thing that you want to work with. I believe this is going to be the toughest problem you're going to see. So that's good. And it's all based on this stuff here. If you can do this and understand it. I recommend you going through this a couple times, getting from delta P equals FT by filling these two in, but it's not too bad, as you can see. It sounds like you already probably got it, but it is useful to just do it yourself at least once. So then how long the bat and the ball were in contact for? Remember, this is a force over a time interval. And so we simply have to solve for T. So
Okay.
what do you get? A standard thing here, right? That's just algebra. You're good on that. And then, well, guess what? We got all those values right up there. But being very careful about your signs. And just like you already went through this a couple times when you did Newton's laws and energy, to make sure your signs are correct, right? And that's related to your picture, which direction did you decide to call positive? I got one more chance to load this thing. I don't know why it keeps dying, but maybe I need a new one. But I can hopefully do the rest with better pictures and stuff. But is there anything that's unclear about that at all?
So when you're plugging it into the equation, so the equation
Yes.
you get is T equals 0.146 kilograms, and then it's parentheses 50 meters per second minus 40 meters per second. Is that right?
It should be. Yeah, it's minus 50 minus 40.
Oh, okay, negative 50 minus, okay.
Yeah, sorry. Yeah.
Okay, and then over 12, negative 1200.
Yes.
Okay.
And so the tip or the trick is to add those magnitudes when you're going in opposite directions. I hope I can show you here what I mean by that, but you see how it was going to the right and then it was immediately going to the left. Well, just add those magnitudes up, as in, not 50 minus 40, it's 50 plus 40. And yeah, there's a minus sign, but I don't want to confuse you if that doesn't make sense.
Yeah, I'm a little confused by that.
Okay, my thing is loading right now, but if you're changing direction, like it is here in this problem, then you just add up those velocities, as in 40 plus 50, the magnitudes of the velocities.
Okay.
But if it's going in the same direction, you want to subtract.
Oh, okay, so in this case, would the equation be different?
Same equation, but then you're using your minus signs differently.
Oh, okay.
I'm sorry, you're asking if this equation would be the same.
Yeah.
Or this one. Okay. Yeah, if you're right, it would be that if it was the same direction. But
Okay.
opposite direction, we want to get the largest number, which means, we're subtracting, but we're adding, it's minus 50, minus 40. It is bringing them together. I don't know why I'm not being clear enough on that.
Okay. And then I want to see if I'm using my calculator correctly. So
Yeah.
Is the answer 0.01095?
Yes.
Okay, awesome.
0.01095. And let me see, we got a large force over. Oh yeah, and seconds. That's right. So it's 10 milliseconds or 11 milliseconds. Makes sense, right? Because imagine hitting a ball. You might know, with a baseball, you might know that better than I do. I don't know, but it doesn't. It's hardly ever in contact with the bat. And so we say, okay, good, makes sense. 11 milliseconds, or 0.01095 seconds. Cool, that makes sense. And notice how large that force is. So I know we're just starting to look at it, but the place where you want to be is to be able to say, oh, look at that large force. The time better be small, because why? My change in momentum, which is just a change in velocity, that's pretty big, right? I mean, the change is 90, because it's going from 40 to minus 50, which is a change of 90. I don't care if it's minus 90 or positive, it's a change of 90. And so, oh, well, yeah, that time better be really short. And then if you can get there, then you're a master and you're good. You're good enough. So again, I think that spend some time on that one, because anything else will just be, here, what's momentum? Okay, mass times velocity. You know what I mean? But that one is actually knowing this equation here, not just delta P equals FT. That's the easy part, right? This is the easy one. That's the easy one, because it's just a two-step equation. Solve for T. Okay, divide both sides by F. But this one is the one that's the test one. That's like the tough one, or the hardest one, even though it's not that hard. You know what I mean? So yeah, that's what you want to practice. Okay. I got number 2 here. I'm going to try. Yeah, 2 and 3. What is that? That looks like conservation of momentum, maybe. Yeah. Do you want to do number 2 or 3 to finish it up on the momentum page? You want to do number 2 or 3 on that momentum page?
Yes, please.
Sorry, do you want to do number 2 or 3?
Can we finish 3, because I don't know if I did that one correctly.
Sure. Okay, so hopefully this works enough. So we got the same mass, cool. We got an initial velocity. When it says pitched, it says, oh, that means that it's the initial, because he's throwing it, or she's throwing it. And we can immediately write that down as we do. Mass, cool. We got an initial velocity. I can immediately call that initial velocity. But now we also have a bowling ball. So then you got to be careful, just as we were before. We got 2 masses now. So call it M sub BB, baseball, or M. What I do is M sub 1. And just remember, oh, 1 is the baseball. Whatever works for you, you have to decide.
Okay.
So M1, and we say, 1 is the baseball. If you need to, write that down, do whatever you need to. And then 2, or mass 2, as many words as you need, is the bowling ball. And so we have a mass 2, of course, that's given. You saw that, I'm sure. And that's whatever it is, 7 kilograms. Makes sense that it's much heavier. And rolled down an alley. Great. So these things are left at, they go at the same time. So that may not matter. But then they want the velocity of the bowling ball. So you might if you need to, another subscript here to say the initial velocity of 1. Okay, that's the baseball, right? You know, I1 or something like that, whichever works for you.
Yeah.
And then they want to know what, you know, it's to final, which would be subscript like that. And then that'd be your question mark, right?
Yeah.
Okay, that's exactly what you have. Good. And then okay, determine the velocity it needs to move in order to have the same momentum as the baseball. So we're saying same momentum. And it looks like you actually did this correctly. You know, what we're saying here, we want this to satisfy this. That's the trick here. And remember, 1 is the baseball, 2 is the bowling ball. And so that sentence says they have the same momentum. So my equation on the screen right now, that's true, because that's what they give us. Does that make sense?
Yeah.
Cool. Then I'm going to plug in what? Well, it's M1, the mass of the baseball times the velocity of the baseball. So you actually don't even need those initial ones. I thought they were going to do an impulse thing, but it's just this, right?
Mm-hmm.
And what is M1 V1 equal to? Well, M2 V2. Why? Because that's true. I've just plugged in P equals MV for each one. Good on that?
Yes.
Cool. So now I solve for V2, right? So that's easy. I know you can do that very easily and quickly. And you got that. So it would be M1 V1. And then it looks like you just got to plug it in to your calculator there. This is the key though. That's the hard part, or people where they would get stuck, is writing that equation down.
Mm-hmm.
Because the rest of it is just standard, easy stuff. This is algebra. This is our classic extract all the information you need. But this is the key here that they're meaning to trip you up on. And that piece that says in order to have the same momentum, that's what that means. Is that clear?
Yes.
Cool. Again, plug it in and then solve for V2. So, you know, yeah, you get 7 times. Let's make sure here. Yeah, so yeah, do you see the mistake, I guess, on the paper? Because you have M1 times V2 equals M2 times V1. And it should be the other way around. It's M1 times V1.
M1 times V1 over M2.
Yes, yes. So then it would be, does that make sense? I just made an error, or somebody made an error if he did this one.
Okay, so the ones are on top. Okay, so then that would be 0.146 times 27 over 7.
Yes. So they're giving us a velocity of 0.563. Let me triple check myself. I mean, it's definitely M1 V1 equals M2 V2. So then, as you said, V2 bowling ball should be M1 V1 times, yeah, points, and then that's 146 times 27 divided by 7. Makes sense. And then, yeah, so the baseball is moving really fast, as it should. The bowling ball, not that fast. And guess what? The bowling ball has way more mass. That's what gives you that same momentum.
Okay. Oh, okay.
And if you understand that idea that you just said, okay, then that's what we were talking about in the beginning about impulse.
Okay.
Okay. I hope this is helpful. Sorry again for the technical difficulties. Just I hope we got something good out of it though.
Yeah.
Okay, good. As always, it's on. I'll send you the notes, and you can have the video if you need to go back. But yeah, any last questions or anything?
I don't think so.
Okay, good. I will definitely, if you want to prepare, if you need another lesson, this week or next week, I'll definitely be better prepared. I don't know what happened, but so we can get that going.
Okay, sounds good. Thank you so much.
Of course. Take care. Bye.
Bye.